Well, dear students, we have completed a main portion of, chemistry, atomic structure, bonding, and periodic properties. They are main conceptual chapter and fundamental chapter of chemistry. Now, again, we will start. I will. I'm going to start here. Fundamental chapters of physical chemistry. So this is the basic and fundamental chapter of physical chemistry, and all of you should know that this physical chemistry gives you an idea about the different physical processes which are controlling the chemical reactions. Means physical chemistry gives you idea or tool gives you a tool to understand organic chemistry reactions, right? Chemical bonding, and periodic properties, atomic structure, they are core chemistry chapters. But this physical chemistry chapter, this is basic chapter, and this enables you to understand what physical factors may affect the chemical reaction, what are the tools, physical tools we can use to explain fully any chemical reaction, right? So in this regard, this is the states of matter, gases. All of you have definitely gone through different properties of gases, solids, liquids. But here these are the main points of this chapter. First point, I am taking this intermolecular forces. I have already talked about intermolecular forces in chemical bonding. What are the main cause of intermolecular forces? But here I am taking a little bit revision of that, and after that we will start this observable microscopic properties of matter, right? And they are also known as state variable, right? After that, see, this is a very important word, state, here, and definitely I will discuss what is the meaning of state, gas laws, equation of state, and ideal gas behavior. Again, see here, state word is coming, kinetic theory of gases, Graham's law, behavior of real gases, and liquefaction of gases, and critical phenomena. So these are the main points, major points of this chapter. So let's start intermolecular forces. So see, intermolecular forces, I'm taking first point, intermolecular forces. See why this intermolecular forces are so important, and why I have given here privilege to this, to discuss this intermolecular forces, because you know these intermolecular forces may affect the behavior of matter, means solid, liquid, or gas, whatsoever behavior this intermolecular forces affects up to the larger extent. So the behavior of this gas, liquid, solid, it is greatly affected by intermolecular forces. That thus we should know about little bit about this. So intermolecular forces, molecular forces, collectively they are known as van der Waals forces. Means there are many types of intermolecular forces, but all are collectively known as van der Waals forces. Van der Waals forces. And the intermolecular forces or van der Waals forces may be attractive, may be repulsive, because some people may argue, okay, van der Waals forces are always attractive type, but not like that. May be attractive or may repulsive. So another important point regarding this intermolecular forces or van der Waals forces, they may be attractive or repulsive. Means intermolecular forces or van der Waals forces, they may be attractive type or repulsive type, right? So these are the following types. First, dipole-dipole interaction. Dipole-dipole interaction. So see, suppose that we have a dipole, this is negative, this is positive, positive, negative. So there is a attractive force present between these molecules, dipoles, basically polar molecules. So this dipole-dipole interaction, this is observed between polar molecules. Polar molecules, right? So between polar molecules, this is intermolecular force, and due to this force, many of these properties of these molecules, may alter what you are expecting. They will show some different property. So in this dipole-dipole, if we take the gaseous state, this molecule, so there are two situations. When we are taking this, polar molecule in the stationary phase, stationary phase. So when they are in stationary phase, obviously when they are in solid, means if the polar molecules are present in the crystal and they are solid phase, then the force of attraction, between these molecules, force of attraction is varies with r to the power cube. Means this is the distance r. So if they are stationary, then this will vary with r cube, right? When they are in the solid state. But when they are moving, second situation is in the moving phase or rotating phase. Rotating state. Obviously, in gaseous phase, molecules are are always in the random motion. So when they are in this rotating state, means when they are in moving state, then this force of attraction is not this r cube. In this situation, the force of attraction is, the force between these varies with 1 by r to the power 6. So these are the some important points. So this is the first kind of attraction, dipole-dipole interaction. This will observe between polar molecules. For example, if you take water molecule, or if you take HCl molecule, or if you take ammonia molecule. So in all these, means when water is present in its ice in the solid phase, then the force is varies with r cube. But when the water vapor you are taking, then the force will vary with r to the power 6, right? Now see this, after this dipole-dipole, there is a second case, ion dipole. Ion dipole interaction. So when we take ion dipole interaction, this type of interactions mostly we will get in aqueous phase, right? So suppose that this Na plus is there, so ion dipole interaction, delta negative, delta negative, delta negative, delta negative. So this is a dipole, and this is ion. So this is called ion dipole interaction. So in case of ion dipole interaction, the intermolecular force or intermolecular interaction force is inversely proportional to R to the power 4. This is equation 3. So basically, this will observe between between ion and polar molecule, right? So this type of interaction we will observe between ion and polar molecules. Now come to the third case. Third case is dipole induced dipole interaction, right? Dipole induced. So all of you are knowing what is the meaning of induced. The property is not there originally, but it is induced by some neighboring molecules. So dipole induced dipole interaction. Dipole induced dipole interaction. So this type of interaction you will observe between a non-polar molecule, between non-polar and polar molecule. So what will happen when polar molecule is come close to this non-polar molecule, and then there is induction, means polar molecule will induce the polarity in the non-polar molecule. So what we can see, suppose that this is a polar molecule, delta negative and delta positive, and this is a non-polar molecule, spherical, symmetrical. When they close to each other, so see, this is dipole, and this symmetrical molecule also deform and adopts dipole, right? So this is delta negative, this is delta positive, and there is an interaction. So although these interactions are very weak, and sometimes these interactions are also referred as Debye forces. Weak interactions, and also known as Debye forces, and the force is vary 1 by r to the power 6, right? So this is dipole induced, so between non-polar and polar molecule. For example, if you take water vapors, H2O vapors plus helium. So helium is non-polar, perfectly non-polar, and water vapors, it is polar. So in this case, you will get dipole induced dipole interaction, and your force will vary with the r to the power 6, means the distance between these two, many very weak forces, right? So this is dipole induced dipole interaction. Okay. Now, see number 4 type of interaction. Fourth type of interaction is instantaneous dipole induced dipole interaction. Instantaneous dipole induced dipole induced dipole dipole interaction, also known as London dispersion forces. Right here, this type of interaction is called dispersion. So, London dispersion forces. The name of the force basically which is operating between this type of interaction, that is known as London dispersion uh, forces. Now see, this type of interaction is observed between which kind of molecule? So the answer is between two non-polar molecules. This is observed between two non-polar molecules. Non-polar molecules. Like if you take this is a non-polar molecule, this is another non-polar molecule, and when they are in the close vicinity, then one molecule will induce the polarity with the other molecule, and this we can say that instantaneous means this polarity will develop for a moment. In the next moment this will restore, right? Delta negative, delta positive, and we can this is another non-polar molecule, so this polarity will induce, and in the next moment this is again non-polar. So here there is a some interaction. So in this way the molecule, this deformation and reformation of electron cloud simultaneously, instantaneously taking place, molecules are colliding with each other. So this type of interaction basically, this is more prominent in the gaseous phase, and particularly between two non-polar gases. So if someone is asked, okay, what is the cause of the force, intermolecular force between two helium molecules, or in a helium molecule which is perfectly non-polar and symmetrical, so how this force of attraction is present between helium molecule? So your answer should be like this, that there is a instantaneous dipole induced dipole interactions when molecules are come close to each other, then there is a kind of interaction. So this is observed between two non-polar molecules, like between helium like between CH4, CH4, they are also, I mean, non-polar, perfectly non-polar molecule. What is the force? Same, the weak force, it is also a very weak force. So this is also. Now see what is the consequence of this intermolecular force. See, intermolecular force and thermal energy, they can be linked, and thermal energy is, I mean, depends on interactions. So if we observe, then we can, we found that solid, if we move from solid to liquid and from liquid to gas, so this is the order of, increasing order of thermal energy, order of thermal energy. Means in case of solid, there is very less thermal energy compared to liquid, not in absolute sense. Liquid, and in liquid compared to gas. So gases have the highest thermal energy, and this thermal energy is, a kind of, you can say, internal energy for simplicity. Although, internal energy includes all kinds of energy possessed by the molecules in the given state. So, means we can say that in gases, in case of gases, the thermal energy is maximum. But what is the, strength of intermolecular interaction? So, a strength of intermolecular interaction is maximum in case of solids. See, so intermolecular interactions and thermal energy, you can say, both are inversely related. So if you count the interaction, so you will get the interaction order is this: gas molecules have least interaction, after that liquid, and then solid. So this is the, decreasing order of, increasing order of interaction, intermolecular interaction, order of intermolecular interactions. Means the maximum intermolecular interactions are there in solids, least molecular interactions in the gaseous phase, and thermal energy is maximum in gaseous phase, because in gases there are different types of motion is possible, right? Kinetic energy, different types of motion is possible. Gas molecules have translational motion, rotational motion, vibrational motion, and even vibrational motion also contributes in the thermal energy. Some people may say, okay, only translational motion will contribute in the thermal energy. They were wrong. No, not true. See, every motion, every kind of motion, translational, rotational, vibrational, okay, some may contribute more, some may contribute less, but all will contribute in the thermal energy. So since gases have all types of motion simultaneously, with them, means translational, rotational, vibrational, and all are contributing in internal energy as well as thermal energy. Therefore, they have highest degree of thermal energy. And solids have lowest degree of what? Thermal energy, right? So because they have restricted motion, what kind of motion you are expecting from solid molecule? Only vibrational motion, no translational motion, no rotational motion. In liquid, there is intermediate, means translational motion is there, some rotational motion may possible is there, that depends on the viscosity and other factors, right? So gases have the highest thermal energy, and intermolecular interactions are maximum here. So you can say that okay, this intermolecular interactions and thermal energy they are inversely related, right? See, now the next topic will come on this observable macroscopic properties of matter or state variables. This is most important part of your this physical chemistry. And from here we are starting the variables, state variables we are introducing here from here. And all these state variables will use to explain any system, any homogeneous system. So this is very important point. And before going to detail of this, everybody should know about the system. What is a system, and what is the behavior of the system? uh, you have different types of system. So whenever in physical chemistry or in physical science, whenever you talk about anything, definitely, first of all, you should make a picture of your system about which you are going to talk. Suppose that all of you have definitely gone through this pressure and volume relation, that pressure is inversely proportional to the volume, and temperature and pressure relation, right? Like that, all of you have gone. But until or unless you are not specifying your system, you may be wrong somewhere, right? If we are talking about in open system, like in atmosphere, so in atmosphere temperature and pressure are not directly proportional. Temperature and pressure are not directly proportional to in the open atmosphere. When there is a more temperature, when the temperature is high, pressure is low at that region. So where is your Charles law, Boyle's law? How they are applicable? Not applicable. So, to understand any concept, first of all, you have to visualize your system in physics and in chemistry. Don't barely run behind any formula that this formula tells like this. First of all, you should specify your system, then try to apply your formula. So these are the small and valuable points which definitely will help you to understand this physical science. Basically, this is a physical science. So whenever we are talking about any equation, any formula, then definitely that formula may be, restricted for any system, not universally applicable. So you have to know about system. System is basically a specified part of the universe which is under observation. A specified part of universe under observation. Under observation, right? That is called a system. So suppose that a simplest system we can visualize is like this. So suppose that we want to make some study here in this region. So this is our system. So if you take a matter like this, suppose that you have enclosed a gas here, and this is closed here. So this is called closed system. This is closed system, right? So in this system, you have taken a gas homogeneically. This is distributed here. So this is also called homogeneous system. So dear students, in your this class 11th, 12th, IIT-JEE, for IIT-JEE entrance, this class 11th, 12th level, we are talking about mainly homogeneous system. very few occasion we will consider heterogeneous system, because study of heterogeneous system is not included in your syllabus. Very few occasion we have some heterogeneous system. So largely or mostly we have homogeneous systems. This is a closed system. See, as a science student, you have to also bother about what material this wall of this container is made up of, because this will also play important role to control your variables, means to change your variables. So every time you have to also careful that which type of this material is we have taken. Although this is more important in thermodynamics in the next chapter basically, but we will start about thinking these things from here only. So this material, which material is I mean used to make this. So this is also an important variable, and this may change your system variable. So I'm not considering here, I will consider this in the next chapter, but you just start thinking. You know, in this chapter basically we are silent about the material behavior of these materials. But what does it means? It means that we are considering that whatsoever variable we are taking here, whatsoever the I mean variables here, this gas system, this system has, that is independent of this material, but it is not always. Okay, okay, good. So when you take this gas in a system, so whatsoever we are going to talk here, that is about this system, not about the whole universe, right? So every time when you see when you take any system, when you take any study of any phenomena, any concept, any fact, so you have to first visualize your system. Means when you are talking about Boyle's law, so definitely Boyle's law you are going to apply here in this region, and then slowly you can expand your knowledge, your understanding, that okay, if it is applicable here in our this system, then what about if we take our open system, if we take another kind of system, then what will happen? So try to think about the your system where you, at which you are going to apply your concept, right? Now see, this is the simplest example of this system, in which we have taken a gas homogeneous system. So whenever you have taken this material or matter in a system, in a container, uh, you have these four variables always: temperature, pressure, volume, and number of moles, n. So n, it is the number of moles, number of moles. See, this is the default unit of quantity. So default unit of quantity is the number of moles. What I am trying to say, I am trying to say that if quantity is not specified in any question and it is required, then you have to take 1 mole of that matter. For simplicity, don't try to take 1 gram or 1 kilogram or any in any other unit until or unless it is not asked. See here, this is so all of you have this ability to convert this number of moles into grams when it is required in number. So this already all of you have clearly understood this number of moles and related calculations. Now here T, P and V. So see dear students, this these all four variables P, V, N and T, they are called state variables. State variables. And all these variables are required to define the behavior of gas. And all these variables are required to define the behavior of gas. If any one variable is, not mentioned there, so you cannot say formally that okay, this property is like this. So all these four variables are called state variables, right? And all are required to define the properties or behavior of gases. Right? Now see, this is a system. So all four variables, this system has some pressure, some volume, some quantity, some temperature. We cannot say that temperature is there, pressure is there, but moles are not there. It is impossible. Until or unless you don't have matter here, what is the meaning of pressure and temperature? Because these are the variables, although the temperature is not a mechanical property, not related to the matter, it is something different property, non-mechanical property it is, but pressure is a mechanical property. So you cannot say that pressure is there but temperature is not there. So all four variables are always present in a system at every moment. And you know, the fixed values of this P, V, N and T means if you have taken a system, gas in a system, and total all the variables are now constant with respect to time, if then that state is called, that's condition of your system is called state. State means not solid, liquid, gas. These are basically in general word we are telling that okay, solid state, liquid state and gaseous state, but basically the correct word for them is phase. Solid phase, liquid phase, gaseous phase. But okay, it's okay, hardly matters that if you are telling the solid state or liquid state, right? Because you know, existence of solid, liquid and gas somewhere somehow dependent on these variables, basically on these states. So on with temperature and pressure, mainly temperature and pressure, with change in temperature and pressure, basically phases are changing. So what is the meaning of state? State is defined as the fixed values of P, V, N and T, means constant value of P, V, N and T. Means if for a given system like this, all four variables are constant with respect to time, then that condition of our system is called state. So basically state is defined with the constancy of PVNT, not with their appearance or with their other behavior, right? So state if all four variables This is very important point. Whole physical chemistry key concept is this: all four variables are constant with respect to time for given system, then that condition is known as state of system, right? So state is defined with the fixed values of p, v and t. So suppose that if we have p, v, n and t, not p, v, n and t, suppose that we have p1, v1, n1 and t1. This is constant with respect to time, so this is called state 1. What is the meaning of state 2? The meaning of state 2 means if you change certain variables, suppose that we have changes pressure from P1 to P2 by any means, that is independent, no problem. How you are changing, that is hardly matters. P2, volume is V2, number of moles are N1 and temperature is T1. Means we have kept quantity constant, we have kept temperature constant, but pressure and volume are changes. So this is called state 2 of our system. So what is the meaning of change in state? The meaning of change in state is change in the state variables. Don't interpret that changing of solid into liquid is called change in state. Although this type of technology is popular in our society, but try to avoid that. That is called phase change. That is not called state change. So here state 1 and state 2, change in state is basically change in the variables. So sometimes this we can express this in a simple 2D graph. Suppose that this is pressure, variation, and here volume, and here suppose that I have taken some point, one point. So if someone is asked, okay, tell how many variables are there at this point. So suppose that this is P1, V1. So is it possible that N and T are not there? It is impossible. N and T are also there. So, but see, and since N and T are constant, so we can show the variation between P and V, right? So if we take another point here, suppose that here P2, V2 and N1, T1, right, like that. It is impossible that you have two variables in a system and other two variables are absent. It is impossible, right? So this is called state 1 and this is called state 2. This is state 2, right? It has some pressure, some volume different from this, right? So, and whatever path you are choosing from here to here, that is immaterial. So hopefully all of you are clear what is the meaning of state And what is the meaning of change in state? Change in state means change in the variables uh, P1, V1, I mean pressure, volume, temperature, and quantity also may change. But here at your level, mostly you have the system in which there is no change in the quantity. Number of moles are usually constant many times. So this is called macroscopic variables. These are called macroscopic variables. Some microscopic variables are also there. See, here we are not bother about that what is the pressure exerted by one gas molecule. Always we take bulk state of matter, means we will take 1 mole, 2 mole, and then we take the total pressure exerted by the gaseous system. So that's why they are called macroscopic variables. We are not here, going to say that the temperature of one gas molecule is like this. We are telling the average temperature of 1 mole of the gas molecule is this, right? So this is, a little bit information about this state variables. Now let's do some more deep study of these variables, TPVN. So see, temperature and pressure, they are temperature and pressure, they are known as, this is my classification, my interpretation, and definitely I have taken the reference from somewhere, very standard books. So temperature and pressure, they are also, temperature and pressure are also known as potentials. All of you must be aware about electrical potential. All of you must be aware about the electrical potential. So like electrical potential, like gravitational potential, temperature and pressure also known as potential, and this will help you a lot. What is the meaning of potential? Potential means ability to do something. Hmm? Ability to do something. This is not scientific meaning, but this is, a literal meaning which enables you to understand this term potential. Everywhere this is used, in society also used. Hmm? In ability means someone has more ability to do anything, then it is they have more potential, right? So temperature and pressure, they are also potential. So what is temperature potential? First I am taking temperature potential. Basically, temperature potential determines flow of heat from low temperature, from low temperature to high temperature, to high temperature, till the thermal equilibrium. Thermal equilibrium. And you know this, what I have written here, temperature potential, this word it is sufficient to explain this behavior of this temperature. Means if you have two objects, suppose that if you have two objects, object A and object B, and both are in contact, T1 temperature, T2 temperature, and at T is equal to 0 time, this T is time T is equal to 0, T1 is less than T2, right? So what will happen with time? With time you will find that heat will be transferred from here to here. But remember, little bit heat may be transferred from here to here. Means this is a dynamic phenomena, so we cannot consider the unidirectional flow of heat. So there is a, flow of heat. So here I can make a change little bit. Net flow of heat from low temperature to high temperature. Now this statement becomes perfect. So this will takes place, heat transfer will takes place until the both the object, means A and B now both have temperature T, and definitely this T is greater than T1 and less than T2. This T is greater than T1 but less than T2, right? So there is a net flow of heat from B to A. Net flow of heat from B to A. B to A. Till the thermal equilibrium is not established, right? So this is the meaning of temperature potential. Hopefully all of you are clear. And this is called zeroth law of thermodynamics, right? Zeroth law of thermodynamics. Okay. Now see temperature. Let's talk about more about temperature and units in which temperature can be expressed. So temperature is a non-mechanical property. Means this has no relation with the matter. Basically, it is. You can say it temperature difference. It will determines the flow of heat energy. So basically, temperature is a variable which used to explain the flow of energy or to calculate the energy. But this is not a mechanical property, means not related to the matter. So temperature T uh, or thermodynamic temperature, more appropriate word is thermodynamic temperature. Thermodynamic temperature thermodynamic temperature is defined by is defined by the exact value by assigning exact value 273.16 Kelvin to the triple point of water. So this is the, I mean, basically, thermodynamic temperature. Thermodynamic temperature is defined by the triple point of water. What is this triple point of water? See, the triple point of water is the condition of temperature and pressure at which all three phases coexist. Means, triple point is the condition of temperature and pressure condition of T and P at which all three phases of water, solid, liquid and gas are in equilibrium. Equilibrium. That is, coexist. Coexist. Right? Means all three phases coexist. So H2O solid, right? So this is the temperature for this is 273.16. So thermodynamic temperature is basically defined by assigning the exact value to 73.16 to the triple point of water. So if question is asked what is the triple point temperature for water, then your answer is 273.16. And by using this, Kelvin is defined. Kelvin Kelvin, it is the unit of temperature, unit of temperature at absolute scale, and it is defined as the fraction of the fraction 1 by 273.16 of triple point of water. Triple point of water, right? So 1 Kelvin is equal to, you can write, what is the triple point of water? 273.16 Kelvin multiplied by 1 by 273.16. So this is equal to 1, right? So 1 Kelvin is defined like this. So 1 Kelvin, basically it is the 1 by 273.16 fraction of triple point of water. Okay. So this is the Kelvin scale, also called Kelvin, unit of temperature at absolute scale. We have other scales as well to measure the temperature, so called degree Celsius scale. So what is the relation between, and see, one more definition we are using this, Kelvin nowadays. Basically this is the old definition we can say, but nowadays it is defined in terms of Boltzmann constant. Basically this temperature, as in the beginning I have told you that it is not a mechanical property, so it is not defined with the help of some property of matter. Basically this is defined in terms of some constants. So Boltzmann constant means Kelvin can be defined in terms of Boltzmann constant also. Boltzmann constant. This is K. K is equal to R by Na, right? Where R is the gas constant, and Na, all of you are knowing, Avogadro's constant. So basically, Kelvin can be also defined in terms of what? Boltzmann constant, right? Modern definition, it is in terms of Boltzmann constant, but not if you put the value here and then calculate what is the value of Boltzmann constant. So you will get joules. Here the unit of K is unit of R is uh, Newton, liter atm per mole per degree Kelvin, or you can convert this into Newton meter. So joules per Kelvin, you will get the unit here, joules per Kelvin, right? So here finally you will get, when you divide this R with Na, then in SI system we will get joules per Kelvin. So from here also you can define Kelvin. But this is the old definition, and this is the nowadays it is defined, Kelvin temperature is defined in terms of constants, not in terms of some observable property of matter, right? Okay. Now other scales, they are called relative scales. Relative scale, relative scales, we have relative scales. First is degree Celsius scale. Basically this is based on the freezing point, freezing and boiling point of water, right? So freezing point 0 degree Celsius, and boiling point 100 degree Celsius. So this is the reason why in this degree Celsius scale we have divisions between 0 to 100, right? And what is the relation between this and Kelvin scale? So T Kelvin is equal to small t. If for degree Celsius we always use small t. T degree Celsius plus 273.15, right? So this is the relation between temperature and what? Kelvin scale and degree Celsius scale. One more scale, relative scale we have, that is degree Fahrenheit scale, and this scale is also a relative scale. Basically, this is also a relative scale, and it is based on the freezing and boiling point of saturated solution of sodium chloride. Now, see, this is saturated, the relative scale. Fahrenheit scale is a relative scale, and it is with respect to the saturated solution of sodium chloride. And what is the relation between this Fahrenheit scale and this degree Celsius scale? F minus 32 divided by 9 is equal to C by 5, right? So by using this formula you can interconvert this. See, this is initially it was defined with respect to this, but nowadays with respect to water also you can take that freezing point of water is 0.00 degrees Celsius, that is equal to 32 Fahrenheit. So freezing point of water is 0.00, this is equal to 32 Fahrenheit. This also you can take this relation, right? So these are the different scales used in the this temperature measurement, right?